Hello, this is Stat135, Lecture 6. Last time we looked at two ways to find the SE of a MOM estimator. You can either use a non-parametric bootstrap, in which case you can also find a confidence interval for your parameter, or by hand if you're able to find the variance of the MOM estimator. Today we're going to look at another example of doing this by hand, as well as the case where perhaps you can't find the variance of theta hat exactly, but you can make an approximation of it using the delta method. So we'll discuss this, and then we'll start our discussion about maximal likelihood estimators. So here's another example of a MOM calculation and finding the SE. So we have a discrete distribution here, we have some data, and we calculate the MOM estimator, which is given here with X bar for your sample first moment, and because we have data, we can actually get a number. So now we want to find the variance of this MOM estimator, and because of the properties of variance, we can actually do this by hand here, and we see that now we just need to find the variance of X. So there are two ways to do this. You can either use the sample variance, or you can calculate the variance of X by definition of the distribution, expectation of X squared minus expectation of X quantity squared. One took me 3 minutes, the other took me 55 minutes, but both are fine estimates. So let's take a look at another example. X is the exponential lambda, so we know that has expectation 1 over lambda. So we're going to find the MOM estimate and the SE. So the MOM estimate is just 1 over X bar, and the variance of the MOM estimate is the variance of 1 over X bar, which actually I don't know how to find by hand. So instead we're going to do a delta method approximation of this. So now we're going to do a slight diversion on delta method. This is section 4.6. So we have some known random variable. We have a random variable with some known mean and SD, let's say. We have a smooth function around mu, and G prime mu is not 0. So we're going to do a linear approximation for G using the first order Taylor series expansion, which is valid when X is close to mu. So X being close to mu, X has a high concentration around mu when X has a small SD. That's actually the definition of a SD, because SD is the average spread around the mean. So assuming that X has a small SD, we see then that the variance of Y is G prime mu squared sigma squared. So now, when is it that X has a small SD? Well, the random variable that will be of interest to us is the sample mean. So the sample mean, remember, the sample mean, the variance of the sample mean is sigma squared over n. So as long as n is large, the variance of the sample mean will be small. So sample means are great examples of this technique. So here's the delta method. So you have n IID random variables, mean mu, SD sigma, G is smooth around mu, the derivative at mu isn't 0, then the variance of G of X bar is approximately G prime mu squared, sigma squared over n. Sigma squared over n is the variance of X bar. So for us, our MOM estimator is going to be G of X bar, right? So this is assuming that we only have one parameter, and also it's assuming that the expectation of x is a function of theta. Now, so let's say that x is exponential lambda, then lambda hat is 1 over x bar, and so our g of x bar is going to be 1 over x bar in the delta method. So we get that the variance of our mom estimator then is lambda squared over n, and because we don't know what lambda is, we plug in our mom estimator, and we get that the SE of lambda hat is 1 over the square root of n x bar. Here's another example, number 52, chapter 8. I've adapted it a bit so that we also have to find the SE. So we have a density here, and so first we're going to find the mom estimator, so that's fairly easy. We get the mom estimator is 1 minus 2x bar over x bar minus 1. Okay, now that's a function of x bar, right? I don't know what the variance of that is, but this is a perfect application of the delta method. So our function now is just going to be 1 minus 2x over x minus 1. So fantastic. We calculate g prime of mu, and we need to calculate sigma squared, and then the delta method gives me that the variance of my mom estimate is this complicated formula here in highlighted. I don't know what theta is, so I can plug in my mom estimate, and I'm going to get a big complicated formula involving x bar, which I can actually calculate. So next we visited the MLE. So the MLE, we start with some random variables with a joint density. So we make some observations, and we form the likelihood function, which treats the x's as fixed numbers and the theta as variable. And what we're going to do is we want to find the theta that maximizes this likelihood function. So here my x's are fixed and theta is a variable. So we want to find the theta that maximizes this likelihood function, and often enough the xi's are IID, so that we can write the likelihood as a product of likelihood functions for the single variables. And so to find the theta that maximizes this, you would take the derivative with respect to theta, and that's a big complicated product rule here. So what we do instead is we take the log of both sides. The log has the great property that it's monotonically increasing, which means that whatever theta would maximize the likelihood will also maximize the log likelihood. I tried to show that in this picture down here. And so taking the log of the product turns the product into a sum. That's a great property of logs. So I'll write L of theta to be the log likelihood. It's the sum of these log likelihoods for the single variables. And taking the derivative is more straightforward now. And we solve, set the derivative equal to 0 and solve for theta. Theta hat is going to be that theta that solves this optimization problem. So we ended class with just a really simple example. I have a single data point, single observation. Let x be Bernoulli p. So x just takes two values, 0 or 1. And my likelihood as a function of p now is p to the x 1 minus p 1 minus x. You can see for x is 0 or 1 what this is a function of p, and you can see that we either get a diagonal line or in green the line with slope -1. And so let's say that we have the yellow line here. So the question is, what p maximizes this likelihood? Oh yeah, it would obviously be when p is 1, because in that case f of 1p is as large as possible, namely so it's as large as possible. So you can see that when x is 1, the MLE p hat is going to be also 1. In the other case, sorry, oh no, that's right. So sorry. So in the other case, when x is 0, in that case, it's the green slope here -1. So then we have, when x is 0, we can see that the MLE is going to be 0, because that is when f0 given p is as large as possible. So you can, of course, do this just using calculus, and so let me show you that. So the likelihood of p is p to the x 1 minus p to the 1 minus x. The log likelihood then is given here. We take the derivative of the log likelihood as a function of p, set it equal to 0, and we see that p hat is x, which is what